Welcome to the deep dive. We take your sources, sift through them, and pull out the real gems. Today, we're looking at a sequence you probably know, maybe think is simple. OEIS A000290, the perfect squares.
That's the one. Yeah, fundamentally, it's just n squared. So 0, 1, 4, 9, 16, 25.
Yeah.
You get the idea. NJA Sloan cataloged this one, of course.
Mm-hmm.
But, even that simple N2,
Yeah.
there's a lot going on underneath.
Okay, yeah, let's unpack that.
Yeah.
N2 is clear, sure.
Yeah.
But how are they, formed in ways that tell us more?
Well, what's really elegant is how they build up. A perfect square is always the sum of consecutive odd numbers.
Oh, right, I remember.
Yeah, so 1 is just 1. Then 1 plus 3 gives you 4.
Which is 2 squared.
Exactly. Then 1 plus 3 plus 5, that's 9.3 squared. So each square, it's just the previous one, an1, plus the next odd number, which is 2n minus 1.
It's a neat recursive way to think about it.
It is. And there's another connection to triangular numbers.
Those dot triangle numbers, 1, 3, 6, 10.
Right. A perfect square is actually the sum of two consecutive triangular numbers. So tn1 plus tn equals n squared.
Huh. So they're linked in multiple ways. Interesting.
Definitely. They just keep showing these fundamental connections.
Now, I heard something about their history. Something surprising. Maybe with early computers.
Oh, absolutely. This is a great bit of history. A000290, the squares. This sequence was, believe it or not, the very first sequence ever computed by an electronic computer.
No way. Really?
Yes, May 6th, 1949, on the EDSC machine at Cambridge.
Wow. So the first calculation wasn't something super complex. It was just squaring numbers.
Pretty much. It's sort of humbling, isn't it? The dawn of electronic computing, and they start with n squared, shows how foundational these numbers are.
That really puts it in perspective. Okay, let's shift gears a bit for, the number theory folks listening. What are some deeper mathematical properties?
Well, one key characteristic is about their divisors.
Okay.
Perfect squares, and only perfect squares, have an odd number of divisors.
An odd number. Why is that?
Because divisors usually come in pairs. Like for 12, you have 1, 12, 2, 6, 3, 4. But for a square, say 9, you have 1, 9, and then it's just 3. The square root doesn't have a pair, so it makes the total count odd.
Ah, I see. That's clever.
And connecting to the, let's say, bigger picture, the squares are central to the Basel problem.
Right, summing the reciprocals.
Exactly. 1 plus a quarter plus a ninth plus a 16th and so on. The sum of 1 over n squared. It famously converges to pi squared over 6.
Which is just mind-blowing, connecting simple squares to pi.
It is. And that sum is actually a specific value, zeta 2, of the Riemann zeta function. This function is, well, hugely important in number theory, especially for primes. So the squares are tied right into that beam structure.
Amazing. So what does all this mean for someone just exploring sequences? Is there a sort of concrete, maybe slightly weird property that stands out?
A counterintuitive one. Okay, try this. Take any sequence of consecutive whole numbers, but it has to have an even number of terms.
Okay, like 1 to 10 or 5 to 14.
Exactly. Now split it in half. Sum the numbers in the second half, and subtract the sum of the numbers in the first half.
Okay, so for 61 to 70, that's 10 numbers. Second half is 66 to 70. First half is 61 to 65.
Right. Sum 66 through 70, that's 340. Sum 61 through 65, that's 315. Subtract them.
340 minus 315, that's 25.
Which is
5 squared, a perfect square.
always. And notice 10 numbers total, half of that is 5. The result is 102 squared. It works every time.
That is unexpected, a really neat pattern.
It raises some interesting questions about structure, doesn't it?
It really does.
Yeah.
So we started with simple N2, A000290, and we've seen these elegant ways they're formed, their incredible place in computer history, and these deep ties to divisors, pi, the zeta function.
And even surprising patterns in simple arithmetic.
Exactly. It's quite a journey for such a familiar sequence. So as you look at numbers, maybe think about this. Even the most basic building blocks, like squaring a number, can echo through mathematics, popping up in history, in analysis, and unexpected patterns. It really invites you, doesn't it, to keep digging for those hidden connections all around us.